word root on the board, and I said it was a synonym, so it could be used interchanged for some other words. Does anybody remember what other words are the same as root? Zeros? What else? Solution? X-intercepts, if they're real, right? And I think that's it. Okay, good. So, I know, like, our book calls it rational root theorem, so I'll call it the rational root theorem. When you get to honors pre-calculus, I know that textbook calls it the rational zero test. It's the same thing. Okay? So it's about finding rational zeros or rational solutions or rational roots. So let me ask you this question. In math, what does rational mean? Morgan?
Isn't it like, so like pi is irrational because it like goes on forever?
Yes. Pi is irrational. So numbers, all real numbers. Now we know about imaginary numbers too, but before we only had a box of real numbers. And every real number could be defined as irrational or rational. And pi is irrational because it goes on forever and it never does what? It never repeats. It doesn't follow a pattern. Okay? So does anybody then remember like what kinds of things are rational?
Isn't it a number with like a
Terminating decimals because it ends. It doesn't go on forever. Or decimals that repeat like 0.33333, right? Because 0.333 can be written as what? 1/3, 0.3 repeating, but that could be written as 1/3. So what math word is in the word rational? Ratio, right? If you're in history, you might be thinking about a ration, but we're in math, so we're thinking about a ratio. Okay, so the key here is for the rational root theorem, we're talking about ratios, and ratios look like fractions. So this is a way that we can find zeros that are rational, that can be written as fractions, they can be terminating decimals or repeating decimals, but they are not irrational. So this does not find irrational zeros, which can exist. Okay, an example of that would be like what if your answer was x equals plus or minus the square root of 2? So the rational root theorem is not going to help us find that by itself. Okay, it will get us there eventually. Okay, and it also does not find imaginary solutions. So an example of that would be like, what if it was x equals -1 plus or minus 2i? The rational root theorem isn't going to instantly generate that zero. But the rational root theorem will help us find any zeros that are or could be written as fractions if they exist. Okay, so why the rational root theorem? When I asked you on the warm-up to find a zero, I gave you a polynomial with 4 terms. So you might have checked for a GCF and then you chose factor by grouping. If it was 2 terms, you might look for difference of perfect squares, sum or difference of perfect cubes. And if it was 3 terms, you would guess and check. Well, what if it has 5 terms? Could you factor it? Not anything Miss Cronky taught you. What if it was 3 terms, not quadratic, and couldn't be factored? Quadratic formula won't work if it's cubic. Okay. So why do we even talk about something called the rational root theorem? We use the rational root theorem to make a list of possible rational zeros when you can't factor. I believe at some point it will show up. So this is answering the question, well, what if you can't factor? How are you supposed to find the zeros then? Use the rational root theorem. Don't find the zeros. That'd be too easy, Alex. Okay, now, we'll use the rational root theorem to generate this list of numbers that are possible rational zeros. So we've already talked about what the rational zeros mean. It's got to be something that can be written as a fraction. Someone said whole numbers, or did I do that with that first hour? Did anybody say whole numbers in here? You were going to when I asked what was rational. Okay, so you might know whole numbers, integers. Those numbers are subsets of rational numbers. So if you saw the number 1, that is rational, right? So that you can have nice numbers too. They don't have to look like fractions actually. But what does it mean when I say it's a possible solution? Oops, did I do that? What does that mean when I say possible?
Well, it could give you what could be put in, but there's more than one.
It could be a solution. Isn't that that's what possible means, right? It could be a solution. But it also means it could not be a solution, right? It's possible, but it's not guaranteed. Could be a solution, could not be a solution. So it gives us this list of numbers, and it says why would we use the rational root theorem? We're going to use the rational root theorem to narrow down a list. And now we'll just check these numbers on this list of numbers to check with synthetic division. So there's that whole thing of okay, these could be solutions, but they're not all solutions. How do you know if it's a solution? You're going to do synthetic division. If it's a solution, what will happen at the end of synthetic? You get a zero remainder, a smiley face. Okay? So let's make a little note to ourselves. We're going to check these numbers with synthetic division, and we're going to be looking for zero remainders. Which is why I always put smiley faces in them, because that makes me happy. Those are zeros, things I'm looking for. So now, if I ask you to find a zero, of course, check if you can factor it. But the other option, if you can't factor it, do your rational root theorem, create a list of numbers to check, and then do synthetic guess and check. So sometimes you'll check a number from your list and you'll get a zero remainder. Then you can write that on your list of zeros. Sometimes you'll do synthetic with the list with a number from the list and it won't come out as a zero. And you've got to keep trying. So you don't know if it will work or not. Okay. So last part where we get into what does the rational root theorem actually say. So now we know the why of what we're doing. If a polynomial has rational roots, okay, so those are fraction roots, right? Or whole numbers or integers are also fractions. Then the root will be of this form, plus or minus p over q. So you're going to hear me talk throughout the rest of this chapter. I'm going to be saying things like, oh, did you make your list of p over q's? I'm talking about the rational root theorem. All of the p's are factors of your constant term. Those are usually at the back of your polynomial if it's in standard form. And all of your q's are factors of the leading coefficient. Those are at the front of your polynomial. Okay. So we'll just make the list of possible rational zeros for this polynomial down here at the bottom, just so you have one example. Then we'll do the graphing examples. Okay, so we want to make this list. It's going to have a lot of numbers on it if it has a lot of factors. So we're going to start by doing factors of the constant term. So my constant is 12. Okay. What are factors of 12? 3 and 4, 6 and 2, 12 and 1. Now, I generally like to write them in numerical order. You can write them out of order if you want, so they're next to their factor, but I just write them 1, 2, 3, 4, 6, 12. Those are factors of 12. Okay, those are going to be all my p's. And then I have to find my q's, which are factors of the leading coefficient. Remember, that's at the front of your polynomial in standard form. So my leading coefficient is 3. What are factors of 3? 1 and 3. So in this one, I'm going to do more work than I usually do, okay, because this is like my first example. But like, you have to take every single one of these factors, so you have 6 factors of 12, and you have to put it over 1. So like 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. So I'm going to write that down plus or minus, because that's in the rational root theorem. 1, 2, 3, 4, 6, 12, all over 1. Like each one of those goes over a factor of my leading coefficient. So one of the factors of my leading coefficient is 1. And you should really like simplify those. So do you agree this is like plus or minus 1, 2, 3, 4, 6, 12. Everything over 1 is just itself. Okay. And I always just put one big plus or minus out here so it applies to all of them. I really have 6 positive possible zeros and 6 negative possible negative zeros. So I have 12 zeros there. But I only put them over 1. Now I have to put them over 3. So then I have to do plus or minus 1, 2, 3, 4, 6, 12. All of them divided by 3. Now, if you have other factors in your leading coefficient besides 1, you always have to do this. This is where you start to see like some of the fractions. You only have to write it down if it's a new 0 on the list, if you haven't already written it. So like 1 divided by 3 is new, right? We don't have 1/3 on the list, so I'll add it. And same for 2 divided by 3. That's new. But when I get to 3 over 3, that's really 1, which is already on the list, so I don't have to write it again. And then 4 over 3 is new. 6 over 3 is 2, and 12 over 3 is 4, so I don't have to rewrite those. Yeah. So I just added 3 fractions. That means I have 9 positive and 9 negative possible zeros. So I still have a list of 18 numbers to check. But that's better than not having any idea and checking anything from negative infinity to positive infinity and looking for 0 remainders. If a rational 0 exists, it will be on this list. No other rational zeros are allowed. They have to be on this list.
So you keep it 4/3 and don't do 1.
I keep it what?
So do you keep it 4/3 or?
I write 4/3, yeah.
So we don't do 1 and 1/3.
No, because if I were really going to have to check 4/3 in synthetic division, I would be much happier doing like 6 times 4/3 than 6 times 1 and 1/3. Okay. So let's do the example on the first slide. So you can see, like, let's use this to do our synthetic guess and check. Open up your notes. Okay, now we're kind of like past the middle of our chapter, but this is a long chapter, so it's good for us to go back and review what we learned on day 1. So I'm going to go a little bit out of order. I'm going to start with B. What is your degree? 4. What is your leading coefficient? 2. What type of polynomial is this? Quartic. And how many total solutions should there be? Same thing as total zeros. There should be 4 because that's equal to the degree. What about maximum number of terms? 3, that's the degree minus 1. And what would be the y-intercept for your graph? Negative 30. So I write that as an ordered pair, 0, negative 30. And then if I'm doing end behavior, I want to look at B and C, my degree and my leading coefficient. So if I'm doing the right side as x approaches infinity, what do I look at? The leading coefficient. Is the leading coefficient positive or negative? Positive, so the right side rises, goes up. So y goes towards positive infinity. Okay, when the leading coefficient is positive, the right side rises. When the leading coefficient is negative, the right side falls. And then I'm going to say as x approaches negative infinity, and I would say, what do I look at for that one? The left side? The degree, and I'm asking myself, is my degree even or odd? This one is even, so the left side does the same thing. So since this one's going towards positive infinity, my left side is also going to positive infinity. So while I don't necessarily know what's happening in the middle, if I were this polynomial, my arms would look like this right now. So I at least know that. Okay, now I want to get to, like, normally we would have just jumped to, like, let's make a table of values, right? But we practice with factoring. We would factor, find the zeros, and add all that stuff in. Well, today, look at that polynomial. How many terms does it have? 5. Do you know how to factor 5 terms? No, I can't factor that polynomial. So I can't factor. I'm going to go to my rational root theorem, make a list of zeros to check, and then I'm going to start checking them and hope for smiley faces. Okay, so let's make the list of possible rational zeros. Go to your constant. Oh, 30. Got to list all the factors of 30. I just kind of worked my way up. Like 1, 2, 3, not 4, 5, right? And then I just got their pair, their match. So that'll be 5 times 6, 3 times 10, 2 times 15, 1 times 30. What are factors of your leading coefficient? 1 and 2. So this time around, I'm not going to write them out separately. I kind of do that part in my head. But I'm going to take all the red numbers and put them over 1, which will just give us the red numbers, right? So in my list, I'll have plus or minus 1, 2, 3, 5, 6, 10, 15, 30. That's all of the p's over 1. I gotta finish this list. I'm gonna go back and grab all of my p's and put them over 2. I only have to write them if they produce a new zero that's not on the list. So like 1 over 2 is new. 2 over 2 is 1 which is already on there. I don't have to rewrite it. 3 over 2, 5 over 2. You might notice only the odds are going to produce new ones because they're going to be fractions. 6 over 2 is 3, 10 over 2 is 5, but 15 over 2 would be my last one to add to the list. Okay, so all this does for us is say, check these numbers with synthetic, because if you get a 0 in synthetic, it's going to be one of these numbers. So if you are checking 5 right now, you're on a fool's errand. 5 will never work for that polynomial, because it doesn't have the right plus or minus q over q value. I will also give you this hint. You know, I suppose I can be a little bit, I wouldn't say mean, demanding of your intellectual skills at times, right? That may be how you feel. But on a quiz or a test, I'm not going to have a list of this many possible rational zeros and have the only one that works be 15 halves. That's cruel. I'm not cruel, right? So I would say this: if you're on a quiz or a test, the number or the list will be short, or you should start at the front of the list. So what number do you guys want to check in synthetic? 1. Okay, so put in your coefficients and we'll check 1. You would probably want to do this with a pencil in case it doesn't work out so you can erase it. Let's see, add down to get 2, multiply, add down, multiply, add down, multiply, add down. Oh joy. I'm so happy. I have found a 0. So I like to make a little list over here for all my zeros. I'm going to say one of my zeros is 1. Now, remember how we've talked about, like, in division, this was x to the 4th. So this is now my x cubed. I could take that polynomial 2x cubed minus 6x squared minus 26x plus 30, because that has 4 terms. I could try to factor it. But like some of you can kind of see ahead, if I take out the 2x squared, I'll have x minus 3. When I factor out of these, am I going to get x minus 3? No, I'm going to get like 13x minus 15 or whatever. So this does not factor, which means, remember the box problems with volume? If you got a 0 right there, you're allowed to build your synthetic. You can divide again. You divided off one factor. Let's try to find another one that works. Okay? So we've checked 1. What else do you want to try? Alex is saying 3. Okay, put 3 out there. That's 2, 6, 0, 0. Oh. I can see already that's not going to work, right? Boo. Not to you, just to the 0. So I'm going to have to restart that one. What else do you want to try? We checked 1 and 3. 2. 2, 4, negative 2, negative 4. Oh, almost. 6, negative 30 is going to get multiplied by 2, and that's not going to be a 0. Boo. What else do you want to try? We've checked 1, 2, 3. Maybe we should check. We could check 1/2. I'm thinking about negative something. Let's try negative 1. Don't forget that those are like numbers at the front too, right? There's a negative up there. Okay, 2, negative 2, negative 8, 8. Oh, that's not going to work, is it? Okay, but let's try negative 2, 2, negative 4, negative 10, 20, negative 6. Has anyone found one in their spare time, Tommy? I led you astray, right? 2, 10, 4, 20, negative 6, negative 30. Oh, joy. So 5 works. Okay, here's the thing that I want, like, I'm okay that we did all this, and you could have tried 1/2. I usually save my fractions for the end because, you know, gotta divide. But in your homework, you're going to feel like sometimes a little frustrated, like I keep trying and trying. You might have a small error. Make sure that you have a 0 for every like missing term in the original polynomial. And then just go slow and keep track of what you're doing. But if you build up this like ability to persevere in your homework, then on a quiz and a test, it's much less stressful. Like you should find it. Like if you test 1, 2, 3, -1, -2, -3, you should normally find 1 or 2 that you need. Okay, or the list will be short and you would already be on 1/2. Okay, so at this point, do you agree that this is an x squared? Because this was x to the 4th. I divided once, I got x cubed. I divided again, so now I'm at x squared. I tell you what, always when I get to x squared, I stop and write it. Because no matter what, I can solve a quadratic. I could either solve it by factoring, or I could solve it by quadratic formula. So I don't keep guessing and checking at this point, although it might work. I'm just going to go straight to the quadratic. What do you notice about all 3 terms right there? This is a 0. They all have a factor of 2. So we'll take out the 2. We have x squared plus 2x minus 3. Do you have factors of -3 that add to make 2? 1 and 2. Oh, factors of 3. -3 and, or +3 and -1. Not factors of 2. Factors of 3. Did I check -3? I must have done my math wrong. I can't remember. Oh, we did 3 but not -3. Okay, well I was gonna get there, right? Okay. Alright, so then that's gonna produce 2 more zeros, right? X equals -3 and +1. Okay, here's something interesting. Isn't 1 already on our list? So what does that mean? It has multiplicity. 1 with multiplicity of 2, 5, and -3. And if you want to write 1, 1, 5, -3, or 1, 5, -3, 1, that's fine if you want to write it twice. Just note that because it has a multiplicity of 2, it's going to bounce on the axis. Okay, so I'm going to put all this stuff on my graph. Let's see. I had a 0 at 1, a 0 at 5, and a 0 at -3. I have a y-intercept at -30. I know it bothers you guys, but I'm just going to graph it off my graph. I don't care. Just way down there. Who cares? People always get concerned on quizzes and tests when there's not enough squares for their points. Don't care. You can either scale it or you can make it wherever you want it. Okay. And what are my arms doing again? Rising? Okay. So I just got to fill in the blanks. I must come through this point. This has multiplicity of 1. I must come down through my y-intercept. And then I come up. Remember, x equals 1 has an even multiplicity, so I got to bounce. Come down, turn around. What we don't know is, like, where are these low points, right? We're not sure where those max and mins are. We need graphing tools like Desmos or a calculator, or we need calculus, and we don't necessarily all have one of those, so we're fine. It's just like a shape, like a W. Okay. Questions about what we did? Okay, I'm probably not going to do the second example today, so maybe we'll do that one tomorrow as like our warm-up or something like that. This is your homework assignment. It's like 7 problems. And you're only really graphing, it looks like, 3 of them. I think maybe 25 and 31 are asking you to like either find the zeros or just write the list of possible zeros, so follow the directions for those. Tomorrow will be a lot less like, I know the last 2 days with graphing has kind of been a lot, like with multiplicity and end behaviors and everything else. Tomorrow we're just like writing polynomials, so if we have the zeros, can we write the polynomial? That's generally a little bit easier. So we'll kind of take a break.